Hi, this is Jonathan Gardner. We're on section 8.4, the first section 8.4.1 here. Dispersion. So up until this point, we've assumed that epsilon and mu and even sigma, the conductance of materials, or conductivity, I'm sorry, is all independent of the frequency with which you drive a field inside of these materials. And we can really trivially prove that this must not be true based on observations as far back in Isaac Newton time. We have the relationship that the velocity of light has to be equal to 1 over the square root of epsilon mu. And then we can calculate the index of refraction, which is the speed of light divided by the velocity of light in the material. And we expect that when you put light through a piece of glass, that each of the frequencies will behave with uniform index of refraction. But what actually happens is when you put that light through a piece of glass and bend it in the famous prism shape that you've probably seen before, you actually get a rainbow of colors. And the only explanation for that is that the different frequencies of light respond differently, have a different index of refraction in the glass. Now, two similar frequencies have a similar index of refraction, but there's like some range of that. And there's this neat little graph that I'm not going to reproduce here that you can look at in your book. This property, when you have a material that gives a different index of refraction based on the frequency with which you're driving the wave through it, is called dispersion. Okay, and the material is called dispersive. That's what we're talking about now. Now, unfortunately, if you go back to your little string analog and you think about what's happening there, you're not going to see dispersion. Strings don't disperse. They don't have a different frequency dependence, and it's really hard to imagine how you can make that happen. Maybe you can imagine the string is made up of little tiny springs with masses or something like that, and they like to wiggle at a certain frequency, but they don't like to wiggle at other frequencies. But it's really hard to imagine. What you'll notice in dispersive materials, water is a dispersive material. So if you've been learning about waves in a very basic level and you go to your local pond and throw a stone in it, you'll notice that those ripples don't behave the way you expect. It seems like they come and go. What's actually happening is that the velocity is dependent on omega over k, and then you get this experience called the group velocity, Vg, which is just dw by dk, kappa. Okay, and the group velocity, the net result of that is when you strike it with. So if I have a surface here and I basically make a discontinuity there in the middle, then I'm basically driving this at all frequencies. If you do the Fourier analysis of this, you'll get a straight line for the frequencies. And what you'll see is that the waves of different frequencies will complement each other at this group velocity. So you get a bump that kind of travels out like this. It kind of looks like this, where the waves kind of come and go. Another place you might experience this kind of group velocity is when you're playing music and you have two frequencies that are very similar to each other. You'll hear like a beat. You'll hear the beating, the wah 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 wah, that kind of sound, and that comes from the waves are so similar to each other that your ear hears it as a single frequency, but they're subtly canceling each other out at some like frequency in the range of hertz. And so your ear hears the sound coming and going, when all that's really happening is you have two very similar frequencies canceling each other out. Okay, the interesting thing to note is that you may be able to exceed the speed of light with this group velocity, which is really interesting. And there's a wonderful paper written in 1988 about this by Peters called, it doesn't say, it's on page 56 of the American Journal of Physics, whatever. Chapter 50, I don't know. There's a citation in the book here. Hopefully it's in your version of this book as well. Let's talk about these different things. Let's talk about epsilon, mu, and sigma. The conductivity, the permittivity, and the permeability. Mu doesn't vary from the mu of a vacuum. You grab a material that has some kind of mu variation. It's so small you can just ignore it because the epsilon changes so much. So we're going to basically say that mu is constant everywhere. And for most materials that's going to be true. In the one rare case where you find something that has a mu that's very significant, and it actually happens to play a role, you get to write it, talk about that and how about smart you are, or whatever. But we're gonna from now on imagine that both of these constants are actually varying according to the frequency. The next couple sections talks about why this is and what the properties of these functions will be. The explanation will not, it'll be pretty simple, but it will, it's not exactly accurate. There's some subtle things that are missing, and when you go to actually measure the frequency dependency of these things, you're going to see some inconsistencies. But it's a very good model and understanding what's happening here. So with that, that's all I have really to say on this first section. The key takeaway points are that epsilon, mu, and sigma do depend on frequency. That when you throw the rock in the pond, you can see this through the group velocity of the waves. You'll see the ripples, they'll come and go, and they'll move as a group together. And you also see it when you take light and reflect it through a prism. You'll see the rainbow of color, and the only explanation is that the index of refraction for each frequency is different. So, hope this is interesting. Hope this is a bit of a fun respite from all the math-heavy stuff that we've done, and now we're going to get back to some more physics. So, thank you for your time. Bye.